Welcome everyone, welcome family, friends, faculty, and most importantly, our graduates of the class of winter 2019. Before we get started, first of all, a reception will follow the ceremony, to which you're all invited, of course. Our graduates will be called up by name to receive their diplomas. And at that time, graduates may say a few words if they wish. Jose, standing back there, kneeling back there, will take photos of each graduate as they receive their diploma and distribute them afterwards. But family, feel free to come stage and up to the bottom here and take photos if you wish as well. So a few words on your accomplishments. So graduates, you have completed a rigorous course of study and grown as scholars and more broadly as humans. For undergraduates, you've completed Starfleet Academy in astrophysics and planetary science, and for you, Jimmy, you've completed our arduous comprehensive exam process and our graduate core courses. You've learned about everything from subatomic particles to the cosmic horizon, some 13 billion light years distant. But while you've accumulated a great deal of knowledge, the most important skills you have gained are that you have learned how to think critically and scientifically. You've learned how to approach difficult problems and how to learn on your own. You've also embraced the discomfort of the unknown. That in science we disprove or support a hypothesis, but we are always open to revising our theories based on new evidence. Your skills make you much sought after in a wide variety of professions, including teaching, research, innovating, and developing policy. Beyond skills, as part of your liberal arts education here in the College of Arts and Sciences at CU Boulder, you've gained perspective and insight into humanity's place in the universe. Astronomy is an age-old human endeavor and a field that touches us all. You are now experts and ambassadors with a truly cosmic perspective. Congratulations. I want to now introduce Amanda Wimmer-Flint, one of our graduates, and Nick Conant, who will be giving us the astronomy presentation.
All right. Welcome everybody to this momentous day and to the Fisk Planetarium. For how many of you is this your first time in the planetarium? Please raise your hand. Okay, welcome for those of you who are new to this experience. What we're going to do now is have a brief presentation on many of the things that your graduating students have been learning about over the last 4 or so years in their career here as undergraduates. Of course, my name is Nicholas Conant. I'm the theater manager, and I graduated in the APS department in 2014. Amanda back here will be actually operating and doing all this live for us. So what we'll be doing is taking a flight through the universe to explore some of the ways that astronomy has advanced since you began your career as undergraduates. I do want to remind you to please do not use flash photography during the next few moments because it'll ruin the view of the dome and maybe just leave your cell phone muted to make sure we don't have any nasty interruptions. But we're going to start this ceremony in fair and field on a beautiful day. And we're going to start in the traditional way with a sunset. So if you were to go outside tonight and try to go stargazing, maybe you'd see the bright planet Venus setting over the horizon. Maybe someday over the holiday break, you can go out with your students and ask them to point out to you some of the constellations or to tell you about some of the things that we'll learn about in this presentation. Now, if we look over into the western sky, we can see 3 bright stars. And I want to ask the undergraduates, what shape do 3 stars make? No, don't forget your geometry, right? This is, of course, the summer triangle still crowning our sky. And if we look just to the left of it, we can see another shape made of 4 stars, which looks kind of like Colorado in the sky. Maybe it's Wyoming. In fact, this is the Great Square of Pegasus in the night sky. Now, it becomes a little bit difficult to see constellations with all the light pollution in the city of Boulder, so I'm going to ask Amanda to please teleport us to some place without this nasty light pollution. Let's imagine stargazing from a beautiful location. So many things come out, the beautiful band of the Milky Way going through the Summer Triangle overhead. And down in this direction of the sky, we can see perhaps one of the most iconic star clusters in the night sky is the Pleiades, the Seven Sisters. And for those of you who have visited Boulder for only the first time, you may have been seeing this all around Boulder in the form of Subarus, which is the Japanese word for the Pleiades. Now, the Kepler Space Telescope has unfortunately become defunct now in your careers here at CU Boulder. It was observing, what did I say about cell phones? Okay. It was, of course, observing planets orbiting around distant stars, trying to look for the measurable dip in the light of that star when planets moved in front. And it managed to observe a great patch of sky over your right shoulders, or for some of you, your left. And of course, there are many other exoplanetary systems, as we call them. Each bright dot that you see here, or color-coded dot, is resembling one of those solar systems where we have discovered planets around it. So we now know that the sun is not alone in having a myriad of planets. We actually believe that based off these observations, every star in the sky has at least one or two planets orbiting around it, perhaps even more. As we go later into the night, we can see Orion rising higher in the sky, the brightest star in the night sky, Sirius. And if we go to about 2 a.m., we'll get to see the crescent moon rising over in the east. Now, we hope to return people to the moon, and maybe some of you students will actually be helping in this endeavor. Because by 2024, NASA's announced that by 2024 they want to land the first woman on the moon and actually return a crew of humans to the moon, perhaps to begin establishing a permanent presence of humanity on our nearest neighbor. And if we look off to the left of it, we can actually see, I think this is Mars right there, which we may be venturing to in the not too distant future with humans as well. Now, to get to the moon, we would use something like the Orion spacecraft, which has been in development for many years, but we're going to travel back to about 5 years ago when they did a test of the Orion spacecraft, a test launch called the Exploration Flight Test. And so we're going to load up a beautiful rocket launch here that will show you what Orion would look like. So Orion is actually in this space capsule inside the nose cone, and this is a Delta IV Heavy rocket. This test ended up being 95% successful, which is, well, that's quite a success. If you got 95% on all of your tests, I'm pretty sure you would be happy graduates indeed. Let's listen in on mission control as they launch the Orion spacecraft. Going to keep Orion going to something like 18,000 miles an hour to get into orbit above the Earth, where it'll be orbiting about once every 90 minutes. Now, of course, a trip to the moon would take many days, and a trip to Mars would take something like 6 to 9 months. So any rocket that we launch to the moon or Mars will actually have to be larger than that one. Now, what we'll be doing is blasting off of that rocket up into orbit around the Earth and looking back down at our place on Earth. I always feel like we need dramatic music at this point. Da, 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 da. Thank you, Tito. Bum, 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 bum. Now we can look out. We can look down at where we are, right there in Boulder, Colorado. As we fly away from the Earth, we'll get a sense of our scale in the universe. So everybody say, "Bye, Earth." The moon is our closest neighbor, and like I said, it'll take an astronaut about 3 days to travel there using conventional rocket technology. And it's about 1 light second. So a beam of light would take about 1 second to reach the moon from the Earth, and about 1 second to return. That's the furthest humans have ever traveled, personally, in outer space. Now, the sun is about 8 light minutes away, meaning that at the speed of light, it still takes 8 minutes for light to reach the Earth from the sun. Now, even at such colossal speeds, we can imagine something like the Parker Solar Probe, which actually is the fastest human spacecraft ever launched. And how fast is it going? Well, it's going about 500,000 miles an hour at top speed. Woo! And so we can show you this clock down here, and it's going to get closer to the sun than any spacecraft ever before. And so right about there is where it is today in its orbit. And you can see that it's getting closer and closer to the sun, and it keeps continuously receiving passes by Venus, where Venus is adjusting its orbit to go closer to the sun than ever before. Now, Parker Solar Probe is just one of the spacecraft that have been launched recently. We'll zoom away now to remind ourselves of all of the myriad of missions launched to Mars, especially ones like InSight, which is searching for Mars quakes on the surface of Mars now. Or maybe say goodbye to a lost friend like Opportunity, which landed in 2004 and was roving around on Mars for 15 years. RIP Opportunity. It was finally declared defunct in, I think it was earlier this year or late last year, due to a dust storm covering its solar panels. Now, Juno spacecraft has been taking fantastic, unprecedented science of Jupiter, and has actually returned such amazing pictures that we're going to zoom into Jupiter and look at just how high quality Juno has provided us this atmosphere, the largest planet in the solar system. This is Juno almost to scale. Now, Juno's managed to take this beautiful array of images of Jupiter, showing us the clouds in all their swirly majesty. And we're actually going to wrap all this around on the dome. So we're going to do a little planetarium trick of showing you all of what Jupiter would look like wrapped around onto our dome. So hold on tight. Woo! We can see the beautiful bands and belts zipping around on Jupiter. The reds and yellows are more toxic clouds like ammonia and ammonium hydrosulfide, while the whites are water vapor clouds, so just like the clouds you have here on Earth. Juno is not the only spacecraft to make amazing discoveries in the last 4 years. We've also, back in 2015, launched New Horizons off to Pluto. Actually, I should say it finally reached Pluto after a 10-year journey there. Now, Pluto at the time of New Horizons launch was the most distant planet in the solar system, but now it is the king of the dwarf planets. Pluto, we know, has 5 moons orbiting around it, and as New Horizons was on its journey there, it managed to capture a stunning array of pictures of part of the planet, or should I say dwarf planet, and it zipped off to another body. But let's go visit Pluto first. So we're trying to load up all of its beautiful moons, and we can see that they're in fact so large that the center of mass of this system is outside of Pluto itself, that These moons don't go around Pluto per se. Pluto and the moons go around a center of mass outside of the body. We can see the iconic heart of ice on Pluto, as New Horizons saw as it went past. We saw a strange world that we didn't expect to be nearly so active, but there are ice mountains and volcanoes. We see very large structures of glaciers moving around on this body. Definitely a surprise, to be sure. New Horizons then continued on past Pluto to pass a body known at the time as MU-69, or as it is now called, Arrokoth. This is a contact binary. Ask your students what that means at dinner tonight. It looks kind of like a rubber duck or a snowman, but this is the most distant body ever visited by one of our spacecraft now. So far and distant from the sun that it is part of a region of the solar system that we now call the Kuiper Belt. It's like an icy version of the asteroid belt. Pluto is a part of this distant belt and actually has so many other companions joining it in orbit around the sun, out beyond Neptune, what we sometimes call trans-Neptunian objects. There's much more that happened in the solar system than I have time to cover here, but let's zip away from a solar system and remind ourselves of some of the interstellar astronomy that has happened. Spacecraft like Gaia and TESS have been launched, mapping nearby stars. In fact, Gaia has mapped 2 billion stars in our local galaxy, and TESS here has been mapping exoplanets, very similar to the way that Kepler Space Telescope has been mapping, but it's going to do it for the entire sky, not just a small fraction of the sky. And together, TESS and Gaia are giving us a view that there are so many more stars around us than we ever imagined. In fact, our whole galaxy, we believe, is made up of something like 200 billion stars. Our sun is just one of those stars. We can see the bright central hub of the Milky Way and its spiral arms. Our sun is not nearly located near the center or toward the outskirts. It's about halfway in between in what we call the Orion Spur. Here's our sun. Our galaxy is not alone, though. There are numerous other galaxies nearby. In fact, the large and small clouds of Magellan you can see if you travel to the southern hemisphere. Woo. We've got the local cluster of Andromeda, which has its own posse of galaxies going around it. And we're going to leave our Milky Way behind and our whole local group and take a look at some of the more distant and perhaps impactful discoveries in astronomy made in the last few years. So every dot you see here is another galaxy. We're showing you the nearest 30,000 galaxies or so. And the Hubble Space Telescope, with help from many other surveys, has been able to actually image many of these galaxies. So we're going to provide pictures to these points. We just did a close flyby of Centaurus A. As we fly further out, we can actually see the structure of the universe now as these large swaths of galaxies and voids in between. And in fact, the largest collection nearby is called the Virgo supercluster, which we're conveniently going past right now. That's where that beautiful view of a black hole was first imaged for the first time this year. At the heart of that cluster is a galaxy, M87, and this powerful jet emanating from the black hole deep at its core. For those of you who don't remember this picture, let's bring up the Eye of Sauron, which is what this black hole picture looks like to me. This is the first time astronomers have ever directly or nearly directly imaged a black hole, especially in such detail, to see the swirling gas moving around the black hole. Now, of course, there's perhaps the most significant field, the most significant accomplishment, I should say, in astronomy was made just a few years ago with the discovery of gravitational waves, which unlocks a whole new way for astronomers to understand the universe. that when distant black holes or neutron stars collide and merge, they release so much energy that they ripple space-time. So here we've got a pair of black holes that are in-spiraling. And as they merge, you can see the warping of space-time around them from their immense gravity warping space, but their actual merging then sends out a cascade, a ripple through space that propagates for billions of light years and eventually can reach our observatories here on the Earth that measure those sorts of things. We also can remember neutron star collisions do the same thing. And this simulation of a neutron star merger also will show us, let's try that again. Sorry, we need to try that once more. There we go. These are the degenerate cores of stars that have died. And as they collide, they release so much energy that they produce new elements that we thought were only made in supernova explosions. But we now believe that many of the elements in the periodic table that have made it into our Earth and made it into our bodies actually originated in neutron star collisions. Something that we thought, say, only 4 years ago would have been strictly from supernova explosions. So we've seen the local universe, and I'd like to now return back to the Earth to get a sense of how small our Earth seems to be and just how fragile and precious it is in the immensity of space. Because each of these dots we show you here is about 100 billion stars. And in the last few years, cosmologists have updated the number of galaxies they believe there are in the universe. When I was an undergraduate, I was told there are probably some 200 billion galaxies in the universe, each with about 200 billion stars. But now cosmologists think that perhaps there are as many as 20 trillion galaxies in the universe. So for 20 trillion galaxies and 200 billion stars apiece, we're talking something like 4 septillion stars, is it? So many, that's like a trillion stars. And if each of those stars has just one planet around it, then we're talking trillions upon trillions of planets in our universe. And we know that each star has on average one planet, but our sun has 8. So the odds become, well, you can do the odds yourself. Ask your undergraduates and graduating students how they would figure out how many Earth-like planets are there in the universe. Just how special are we? Within our own solar system, we know we won't find any habitable place for humans to live on Venus in the near future, and even Mars seems kind of like a dream because it's so cold, icy. Can't even breathe the air there. Helps me to appreciate the Earth even more. Because everyone you ever knew, and everyone you've ever known, your ancestors, they all knew the Earth. But graduating students, you know how to put the Earth into context for them. You know where it fits in the whole universe, just how special life on Earth even is. So I'd like to leave you with that thought as we now return to the surface. Perhaps you'll go hike a 14er or explore the mountains over your break. But I'd like to return now to this ceremony and congratulate you for knowing astronomy. Thank you.
Thanks, Nick and Amanda, for that wonderful presentation. I'd now like to introduce Professor David Brain, who's our Associate Chair for Undergraduate Education, and he's going to be calling the names for our undergraduate and our one graduate student graduates.
Okay, welcome to the graduates and to the faculty and to the family and friends of the graduates, and also to the future graduates of the astronomy department at the University of Colorado. Got it? Okay. Graduates, here's how the process will work. I will call your names one at a time. Professor Halverson will give you your diploma. There's a photo opportunity at that point. Jose will definitely be taking a photo, but family and friends and future graduates of the University of Colorado are also welcome to take photos at that time. And then there's a microphone here. If you'd like to say a few words, you're welcome to do that. We have a lot of graduates today, so I'd like you to limit your comments to 10 to 12 minutes apiece. And this is your opportunity to pay the faculty back for all the time you've had to sit and listen to them. Okay. So the last thing is applause. Out of respect for all the graduates, please do it. That's it. Okay, so everybody got it? You're ready to go? Okay, and also we have about 9 undergraduates who have graduated from the department as of this semester. And out of respect for all their hard work, we're going to read every name, whether or not they were able to attend the ceremony today. Some people had to get out of town quickly. And we're going to applaud for each one of them. Ready? Thomas Black. Andre Chirano. You ready? Carlos Cruz Arce.
Oh, it might not be actually.
Check 1 2 1 2. First of all, I'd like to thank everybody for coming out. I would like to thank my parents and my sisters for always supporting me, my players and their parents for being just the biggest blessing of my life. My professors, my mentors, Zach and Jessica Roberts, our astro mama, Susan. And most of all, I'd like to thank my ancestors, the original people of Mexico, for reminding me that when I was ready to give up, I thought about them and how they built amazing structures using the stars, using astronomy and geometry. And yeah, thank you so much to everybody. Thank you.
Zhang Bruce Huang. Tyler Kadlik.
I want to thank my parents, my mom, Hope, and my dad, Fritz. Without them, I wouldn't be here. And I want to thank all my professors for helping me when I had problems and just couldn't get a problem done and stuff. And wow, this is cool. Thank you.
Shafiq Saidek. Bingyi Chin. Shay Raposa.
Thank you. Oh. All right. Woo! Congrats to all the other graduates. I want to say thank you to everyone in this department. These have honestly been some of the best years of my life here in Boulder. Thank you to my dad and stepmom who are here today for supporting me and all that corny stuff that we don't need to do. Yeah, next step, PhD.
Kent Ritchie. Tyler Schooley. And I'll editorialize and say that Tyler just completed his second lap through college. Logan Snyder. And with that, let's have the undergraduates stand, please. And let's congratulate them once more. Thanks. Okay, time out. We have to figure out what happens next. We're completely prepared. Okay, so now we're going to transition to our master's and graduate students. And we have one master's student receiving his diploma at this winter graduation ceremony. And so I will call his name, and then the festivities will continue from there. James Negus.
So James's advisor is Professor Julie Comerford, and she is unable to come on the stage. Is she here? Julie, oh, she's back there with a baby. I can take over with the childcare if you want to come up. Okay. All right. So first, I'm gonna hood Jimmy if I can figure out how the hood works. Good luck. I thought I knew how these worked, but maybe not. Now I'm going to say a few words on Professor Comerford's behalf about Jimmy, and then you're welcome to say a few words after that. So Professor Comerford writes, for Jimmy's Comps 2 project, he dove into some of the most complicated data in astronomy, integral field spectroscopy. Instead of a single image of a galaxy or a single spectrum of a galaxy, the integral field spectroscopy that Jimmy used provides an image and dozens of spectra of each individual galaxy. He analyzed these complex data for 6,000 Sloan Digital Sky Survey galaxies in search of emission lines so faint that many people said they couldn't be found in this data set. But Jimmy found them, increasing the known number of these coronal lines by an order of magnitude. The coronal lines are important indicators of high ionization sources in these galaxies, including ionization from active supermassive black holes and stellar shocks. This work earned Jimmy a high pass on his Comps 2 exam.
Thank you everyone for coming out today. It's truly an honor to be here and represent my class. First and foremost, I'd like to thank my mom and grandmother. They have truly been the pillars in the storm as my comprehensive exams and the trials have come. They've always remained really my foundation and my bedrock, so thank you very much. I'd also like to thank Julie Comerford, my advisor, who through my stubbornness and ups and downs has continued to support me, and that really is invaluable for me. And it really is what drives me to continue on and to be the best researcher I can be. I'd also like to thank a few of the professors. Zach, your smile and your enthusiasm is always great, especially when I'm having a down day. Thank you for your support. Andrew Hamilton was actually, before I entered grad school, we talked for black holes for about 3 hours in his office. But the important thing there was, having not been admitted, he still gave me that time to really honor my input and to really encourage me to continue on. So thank you, Andrew, for your continued support as well. Nick, of course, thank you for your being a role model in teaching, especially with undergraduate astronomy. You continue to be an aspiration for how I want to teach as well. Same for Doug. I had the opportunity to TA for Doug this semester. Doug, your guidance, your philosophy, is really, really unique, and I hope to adopt a lot of your traits if I am fortunate enough to teach one day. John Keller, who oversees a lot of the FISC operations as the director, has also been an invaluable support for me. He's helped me re-envision the scale model solar system. So as you exit FISC today, you'll see an existing scale model solar system, and we're working on completely upgrading the model, and John has been a great pillar for that transformation. So yeah, my journey, you know, I won't get too into it, but it began in 11th grade when I built my first Dobsonian telescope. And really, since then, I've been on an endless pursuit to just understand the cosmos. That's been the driving factor for me, and it continues to be what inspires me. I love helping others, encouraging others, and if research and academia is the vessel for which I can do that, then I will do that wholeheartedly. Thank you to my colleagues, my peers, Dennis and Sam. Your support has always been great. Sam and I frequently give outreach talks. We've gone to a few senior homes and talked to a few multiple sclerosis patients. Thank you for your support in that regard as well. My journey is just beginning, and I'm very excited for where it will end up. Thank you, FISC staff, for continuing to be there as a support vessel as well. Thank you, everyone, for coming.
All right, so this concludes our ceremony. Thank you all for coming, particularly friends and family. Following this closing, we will be having a reception out in the lobby. But before that, the students and faculty should meet outside for a group photo to celebrate the occasion. So parents and family, please allow the students and faculty to exit, and then we'll see you out in the lobby. Thank you all for coming.